We are from Ashok Leyland, Chennai unit. We are proud to present the IAQ Quality Sustainability Award 2025 Global Round. This is our project title, Iron Ore Extraction from Grinding Waste. This makes a significant contribution to the carbon footprint reduction, circular economy and aligns with SDG goals 9, 12 and 13. The overall generation of grinding waste in India found to be average of 50 lakh metric ton of grinding waste. At Ashok Leyland, we take immense pride in our legacy that spans over 75 years since our founding in 1948. Our vision is to be a top 10 global CV player. We are headquartered in Chennai, Tamil Nadu. Our facilities are strategically located in Tamil Nadu, Maharashtra, Rajasthan and Uttarakhand. Globally, our presence spans 49 countries, reflecting our focus on strategic international expansion. We have manufacturing, assembly facilities, including e-treatment at Ennur facility, Ashok Leyland. Let me define the business context. These are the three pillars of sustainability: healthy environment, healthy economy, healthy society. AL focuses on carbon footprint reduction, energy conservation, and our team focuses on hazardous waste reduction. As a team, we are committed to minimizing hazardous waste at our Ennur facility. We adapted a prioritized approach to waste management, identifying and addressing the most critical waste streams first. Last year, we successfully completed the paint sludge recycling project. This year, we have taken up grinding sludge as our next priority, launching an innovative recovery project to further reduce hazardous waste and promote sustainability. The grinding sludge disposed is in 5.2 category of hazardous waste. We have authorized recycler by name Jepil at Ranipet, 160 km away from our factory. They are engaged in co-processing of hazardous waste and they supply this processed hazardous waste as an alternate fuel to the Dalmia cement factory, which is 300 km away from our factory. The annual disposal quantity of grinding waste is 120 metric ton and disposal cost is rupees 10.9 per kg. We focused on gear shop, the grinding waste generated in forged steel components machining process. We have 23 machines which uses coker cool water base to generate water based grinding sludge and 11 machines which use neat oil macron to generate oil based grinding sludge. The grinding waste consists of workpiece part EN353 etc., grinding wheel which is silicon base and coolant with chemical. We also identified the presence of hazardous substance classified under R65 and R66 in the grinding waste, indicating that the material poses potential health and environmental risks. To better understand the composition of the grinding waste, we submitted samples both water-based grinding sludge and oil-based grinding sludge to the National Testing House Laboratory. The analysis revealed a significant presence of ferric oxide Fe2O3 in the sludge. The grinding waste primarily contains silicon, nickel, Fe2O3, chromium and Al2O3. Laboratory analysis revealed that ferric oxide constitutes about 59% of the waste, representing a significant source of iron. Based on this finding, we decided to extract iron from the grinding waste. Our team used the TRIS methodology to identify breakthrough opportunities that could unlock the potential for resource recovery from grinding waste. We have identified the breakthrough factor as transforming the defect into resource, and also we identified the homogeneity principle, which is the material compatibility in interactions. We used periodic table to identify the properties of 5 elements: silicon dioxide, nickel, Fe2O3, chromium and Al2O3. We adapted the 3I approach: imitate, improve and innovate. As a part of this, we revisited the composition of grinding waste to reduce impurities by studying the presence of nickel, chromium and aluminum. We analyzed all 5 elements in the grinding waste to determine feasibility of thermal process, and the same is studied and tabulated. Out of this, Fe2O3, which constitutes 59% of the grinding waste. Aluminum can be separated using a thermal process, while silicon, nickel and chromium require a chemical process for effective separation. Our team decided to separate unneeded silicon dioxide, aluminum, chromium, nickel, which constitutes 3%, and extract iron Fe2O3, which is 97% through mechanical and thermal process. So as a part of solution development, we approached the magnetic separation method. Since magnetic separation was not giving desired results, as slag and iron was attracted and found to be time consuming, it was dropped. So we gone for an alternative solution, pyrometallurgical process as a viable solution. After evaluating alternatives, we finalized the pyrometallurgical approach and implemented the following steps in our project. As a first step, collection of grinding sludge, next dewatering, demoisturizing, decarbonizing, deoxidation, sintering, slag separation and finally the iron extraction. So in this innovation model of POC at stage 1, we have collected the grinding sludge and categorized it into oil-based grinding sludge and coolant-based grinding sludge as shown in the slide. In stage 2, in the dewatering, we have gone for the dewatering of the grinding waste, as thermal drying is an effective sludge treatment method for dealing with the large volumes of sludge. In stage 2, for oil removal from the oil-based grinding sludge, we used magnesium chloride and alum in the ratio of 1:1000, and alum slurry with the hazardous waste. We could see the success rate. Oil was cracked and removed from the hazardous waste grinding. Further, you can see the separation of water-based grinding sludge and oil-based grinding sludge. You can see the oil removal process of waste-water chemical ratio of 1:1:0.1 as shown in this. In stage 3 POC concept, we can see the demoisturizing. The grinding sludge spread in the big trolley for demoisturization. In POC stage 4, the decarbonizing process refers to the removal or reduction of carbon content from metals, typically during refining or recycling operations. You can see the proof of concept here. And at stage 5, deoxidation done, which refers to the removal of excess oxygen from molten metal. This is achieved by adding substances with high affinity for oxygen, which forms oxides that are either gaseous or easily converted into slag. In stage 6 POC concept, sintering done. Sintering is a thermal process where fine particles of metal or ore are heated to a temperature below their melting point until they bond together. Stage 7 melting involves the heating the material to a temperature above its melting point, converting it into a liquid state. The process concludes with slag separation followed by iron recovery, which is then converted into steel shot coins and bars as the final product. We made a trial one. We took 500 gram of iron ore, placed it in a graphite crucible and attempted remelting in the furnace. The material required extended heating time but did not achieve a fully liquid state. A significant amount of slag was formed and only a small quantity of metal was extracted. Based on our observation, the oxidized nature of the material prevented it from melting directly in the induction furnace. We decided to add the steel shots in stage 8 POC concept and made a trial 2 observations. Out of 900 gram of material, 874 gram was recovered with the remainder lost as slag and fumes. When 850 gram of steel shots were melted together with 50 gram of iron ore in the crucible, the 50 gram of iron ore yielded approximately 20 to 25 gram of metal. This indicates a metal recovery rate of about 40 to 50% from the iron ore. In stage 3 trial, we made an observation. 5% catalyst steel was utilized to optimize the process for large scale iron. Achieved 80% iron recovery efficiency, while 20% of the material was converted into slag. You can see the big iron bar as shown in the slide. This innovative project of iron from grinding waste was reviewed by Central Pollution Control Board and they have given the approval. You can see the expert committee giving the approval, and we also further discussed in the Tamil Nadu Pollution Control. Our team first time in India converted 100% this grinding waste, which is hazardous category, into a non-hazardous category. We have achieved the 52% recovery of iron in trial 1, 70% recovery of iron in trial 2, 80% recovery of iron in the large scale implementation in trial 3, and remaining 20% is the slag. Really, this is the breakthrough results. You can see the entire hazardous category converted into non-hazardous category. 80% of the iron which is non-hazardous and 20% of the slag which is non-hazardous. This is the breakthrough result. Let me brief on the savings and sustainability summary. Total generation is 120 tons per year of grinding waste. The current disposal cost is 10.9 per kg. The annual disposal expense is around rupees 13 lakhs. If you look at the iron recovery rates, initially we got 52% at foundry end node. Later in the vendor 1 and vendor 2, we had a 70% and 80%. So the expected recovery was 96 tons per year, that is around 80%. Revenue potential, when you take the iron scrap reference value of 32 rupees per kg, our annual savings stands out to 30 lakhs. Look at the environmental benefits. We have eliminated hazardous waste incineration, avoided 160 km transportation to authorized recycler, reduced diesel usage and carbon emissions, and circular economy enabled. This is the summary of benefits. The total disposal cost eliminated, incineration not recurred, reduced the carbon footprint, we promoted circular economy. We are proud that we have done this project in our mother plant Ennur. In the context of business environment, as a part of horizontal deployment, we also found the hazardous waste like grinding waste is being disposed across all AL units. That was tabulated here. The disposal cost spent for 178 metric ton on an average was 19.58 lakhs. If you take out the conversion cost of rupees 8 per kg, on an average for 125 tons per year across AL, there is a savings of 40 lakhs per year. Let us look at the carbon footprint reduction. On an average, you can see 25 to 52 tons of CO2 emitted for the mining and extraction of 125 tons of iron was completely eliminated. When you have the iron extraction through coal mining, you can see the lot of energy consumed as shown here. This innovative project was shared to the National Productivity Council, Center for Environment Studies, Anna University, IIT Madras and Delhi. As a part of knowledge sharing session, this innovative project was presented to various colleges and student communities across Tamil Nadu, inspiring them to embrace sustainability and the principles of circular economy. Thank you for the opportunity given for presenting this innovative project. Thank you one and all.